Have you ever been startled by a flash of lightning during a storm? The sheer power of it, splitting the sky in an instant. Now, imagine a lightning bolt 1,000 times stronger than anything Earth can produce. A single flash so brilliant, it can momentarily outshine an entire planet. Sounds like something out of science fiction, right? But this isn't a movie. This is the reality on Jupiter. Welcome, space enthusiasts, to a journey into the heart of the gas giant, where storms rage on a scale we can barely comprehend. Today, we're diving deep into the mysteries of Jovian lightning. For decades, we've known Jupiter has lightning, thanks to the Voyager probes that first detected it back in 1979. But what we've discovered since then, especially with NASA's Juno mission, has completely rewritten the rule book on how planetary storms work. On Earth, lightning is primarily a tropical phenomenon. It's fueled by the sun's energy, which warms the oceans, creating moist, rising air that forms towering thunder clouds. The powerful updrafts in these clouds separate electrical charges, leading to those spectacular discharges we see. Simple enough, right? So, scientists naturally assumed that Jupiter's lightning would follow a similar pattern, clustering around its equator where it receives the most direct sunlight. But Jupiter, as it often does, had a surprise waiting for us. When Juno arrived and started peering beneath the planet's thick cloud tops with its microwave radiometer, it found something astonishing. The lightning wasn't concentrated at the equator. Instead, it was more common near the poles. This was the first major clue that something fundamentally different was happening on Jupiter. Why would the lightning prefer the colder regions of the planet, where there's less solar energy to kickstart storms? The answer lies in the unique way Jupiter's internal heat engine works. Unlike Earth, which gets almost all its warmth from the sun, Jupiter generates a tremendous amount of heat from its own interior, a remnant from its formation billions of years ago. This internal furnace is more powerful than the sunlight the planet receives. This heat rises from the core, creating massive convection currents throughout the atmosphere. At the equator, this powerful upward flow of heat is so strong that it actually stabilizes the upper atmosphere. It acts like a lid, preventing warm, moist air from rising high enough to form the massive thunderclouds needed for lightning. Think of it like trying to boil a pot of water with the lid on too tight. The pressure builds, but it can't erupt. But near the poles, the situation is different. The influence of the sun is weaker, and the internal heat can punch through the upper layers more easily. This allows for the formation of enormous storm clouds, far larger and more turbulent than any on Earth. These are the breeding grounds for Jupiter's super bolts. And when they let loose, it's a spectacle of cosmic proportions. A single bolt can carry billions of volts and reach temperatures hotter than the surface of the sun. For a split second, it can outshine the entire planet's auroras, but the mystery doesn't end there. Juno's observations have revealed another, even more puzzling phenomenon. It detected lightning flashes originating from deep within Jupiter's atmosphere, far below the main water cloud layer where we expected all the action to be. At these depths, around 25 to 45 miles below the visible cloud tops, the temperature is so cold around minus 83 degrees Celsius that liquid water shouldn't exist. And without liquid water, our Earth-based understanding says you can't have lightning. So, what's going on? This led to a groundbreaking new theory involving something scientists have dubbed mushballs. It sounds a bit silly, but the idea is brilliant. The theory suggests that powerful updrafts in Jupiter as thunderstorms are so strong they can fling water ice crystals high into the upper atmosphere, far above their usual home. Up there, these ice crystals encounter ammonia vapor, which acts like an antifreeze. The ammonia melts the ice, even at frigid temperatures, creating a slushy mixture of ammonia and water. This process releases heat, making the slushy droplets, or mushballs, heavier. They then begin to fall back down, deep into the planet's atmosphere. As these mushballs descend, they collide with the rising water ice crystals from below. This is the crucial part. These collisions act just like the process in Earth's thunderclouds, knocking electrons off the ice crystals and separating positive and negative charges on a massive scale. The mushballs carry a negative charge downwards, while the lighter ice crystals carry a positive charge upwards. This creates an enormous electrical potential difference deep within the atmosphere. When that potential becomes too great to hold, it discharges in a flash of what scientists call shallow lightning. This is a completely new type of lightning, born from a process we had never imagined. It's powered not by liquid water alone, but by a bizarre, exotic slurry of ammonia and water, creating thunderstorms in a region of the atmosphere we once thought was calm and uneventful. It explains how you can get these powerful flashes in an area where liquid water shouldn't even be a thing. It's a beautiful example of how exploring other worlds forces us to rethink the fundamental laws of nature we thought we understood. Think about the implications. We're seeing a weather system that operates on principles alien to our own planet. The scale is mind-boggling. Storm systems on Jupiter can be the size of entire continents on Earth. The winds within them can reach hundreds of miles per hour. And at their heart, these mushball storms are generating lightning with energy levels that dwarf anything in our own experience. The Juno mission has truly opened our eyes. It's shown us that Jupiter isn't just a bigger version of Earth. It's a world with its own unique and complex systems. Every new piece of data sends scientists back to the drawing board, challenging their models and pushing the boundaries of planetary science. We're not just observing a planet, we're decoding a cosmic puzzle. What other secrets is Jupiter hiding in its swirling depths? Are there other strange chemical reactions creating weather phenomena we haven't even dreamed of? The ongoing Juno mission continues to orbit the gas giant, gathering more data with every pass. Each flyby gives us a clearer picture of this magnificent, turbulent world, from its powerful magnetic field to its mesmerizing auroras and, of course, its 1,000 times stronger lightning. Jupiter continues to be a source of wonder and discovery. It reminds us that the universe is filled with incredible and unexpected beauty, and that there's always more to learn. The next time you see a storm on the horizon, take a moment to think about the storms on Jupiter, a place where ammonia slush and superbolts paint a violent, electrifying portrait across a planetary canvas. Thank you so much for joining me on this deep dive into Jupiter's atmosphere. If you enjoyed this journey and want to explore more wonders of the cosmos, please hit that like button and subscribe to the channel. Let us know in the comments what other cosmic mysteries you'd like us to investigate next. Until then, keep looking up.